Hello again. Here we have the second example of drawing the root locus. In this case, for this example, GC is provided as KP and GP is provided as 0.05 divided by S times 1 plus 10s. And we want to draw the root locus for the system. However, at the first step, remember that the convention that we have is to express 1 plus rho times n over d in this format. So we have 1 plus rho times s plus z1, s plus z2 up to s plus zm. M is the number of poles that number of zeros that we have, divided by s plus p1, s plus p2, up to s plus pn. Okay, so accordingly we will just convert GC times GP into this format, and you can see it here. Yeah? GC times GP is equal to KP times 0.05 divided by, so instead of writing s times 1 plus 10s, I will write 10s times s plus 0.1. And then we can write Kp times 0.005 divided by s times s plus 0.1. And accordingly, 1 plus rho n over d will be equal to 1 plus Kp times 0.005 times 1 divided by s times s plus 0.1. And then from here we can say that rho is equal to 0.005 Kp, or in other words, Kp is equal to 200 times rho. However, from now on, we will use this 1 plus rho times 1 divided by, this is 1, so 1 divided by s plus 0.1 equal to 0 as the characteristics equation, and we will draw the root locus for this case for different given values of rho, which will result in different values of Kp. Okay, so if we start the process, we see that we have one pole, n is equal to 1, m is equal to, for the denominator we have s times s plus 0.1, so here we have this expression, this value times s, and accordingly m will be equal to 2, m is equal to 0, we don't have any zeros of the open loop system, and then n minus m is equal to 2. So n equal to 2 means that we have two poles, two open loop poles, and we will have two branches for positive locus, two branches for negative locus, and both of the branches will go towards infinity because our r, which is n minus m, is equal to 2. I will draw the negative locus and positive locus here. So this is for negative locus, and we will have positive locus as well here. This is for positive locus. So now we need to figure out how will be the root locus for each case. Yeah? Since we have two branches and two asymptotes, we need to determine the location at which the asymptote cuts the real axis, and then what will be the angle of the asymptote. So for the location for the asymptote on the real axis, we write xa, which is equal to sigma zi minus sigma pi divided by n minus m. And here n minus m is equal to 2. We don't have any 0, so it is 0 minus some of the poles. For the first one, we have one pole at origin, so it is 0. And another pole at minus 0.1. So here we will have 0.1, and accordingly this will be our xa. For the angle, we have r times kCa equal to 2h plus 1 pi, where h is equal to 0 because r is equal to 2 for positive locus, and 2h pi, again h is equal to 0 for negative locus. And accordingly kCa will be equal to, by replacing h with 0, we will have pi divided by 2 for positive locus because r is equal to 2, and 0 for the negative locus. So here will be xa, it is minus 0.05, and we will have two asymptotes. One of them okay, so we will have two asymptotes in two cases actually. Here, instead of having h equal to only 0, we should have h equal to 0 and h equal to 1, because we have two asymptotes. Yeah? So here h is equal to 0 and 1, h is equal to 0 and 1. So 1 as well, 1 as well. And accordingly here we will have two more angles. For the first case, we will have h equal to 0, so from here we will have pi over 2, and if we set h equal to 1, we will have 3 pi over 2. And for the negative locus, we will have 0, and replacing h with 1, we will have 2 pi over 2, which is pi. Okay, so let's draw the asymptotes. For positive locus, we will have an asymptote with the angle of pi over 2 starting here. So this will be one asymptote, and the other one will be with 3 pi over 2. And for negative locus, one will be with the angle of 0 on the real axis, and the other one will be with the angle of pi, again on the real axis towards minus infinity. Alright, now let's see what are the parts of the real axis which belong to our root locus. In the case of positive locus, we already know that the parts of the real axis for which we have odd number of poles and zeros belong to the root locus. In this case, we can see that the part of the real axis between 0 and minus 0.1 belong to the root locus, so it's between minus 0.1 and 0 in the case of positive locus. And for negative locus, we need to have even number of poles and zeros on the right hand side, so it is from 0 to infinity, and it's from minus infinity to minus 0.1. So from minus infinity to minus 0.1 and from 0 to infinity. So these are the parts of the real axis which belong to the root locus, and here I just draw them with the green color. So this will be part of the real axis belonging to the root locus. In the case of negative locus, our branches will start from the pose. One will go towards plus infinity and the other one will go towards minus infinity. In the case of positive locus, the branches will start at the pose, they will go towards each other, and at some point they will depart from the real axis, and we need to obtain what is the value for that point. So it is, as you already know, it is called breakaway point. And we need to calculate the value for that point on the real axis. In order to obtain the breakaway point, we need to solve n prime d minus d prime n and set it to be equal to 0. For this case, our n is equal to 1. Accordingly, n prime is 0. And d is equal to s times s plus 0.1. d is equal to s times s plus 0.1, which is s2 plus 0.1s. Therefore, d prime will be equal to 2s plus 0.1. And if we replace d prime, m prime, d and n in this equation, we will have 0 minus 2s plus 0.1 times n, which is 1. And if we set it to be equal to 0, for s we will get minus 0.05. So this is the breakaway point that we have. So going back to the locus, it will be, if you look at here, for xa we have the same value, so this will be the position at which our branches will depart from the real axis and they will go towards infinity along with the asymptotes. Now we can draw the complete root locus for our system, for the positive locus as well. So at this point the branches will start to go towards infinity. This is a line going towards infinity, and here is another part of the branch. Okay, so this will be our positive locus. Just need to draw it in a cleaner way. And here is what we have for negative locus. Starting from minus 0.1 going towards infinity, and starting from 0 going towards plus infinity. Okay, and then let's see what are the questions that we have for this example. Compute, if possible, the value of Kp such that the step response of the closed loop system is critically damped. So we want to have the step response of the system to be critically damped. This is a second order system, yeah, we have two poles. When do we have the critically damped behavior? This happens whenever the poles of the system are equal and on the they have only the real value. They are located on the real axis. Yeah? So P1 is equal to P2, which is a given real value minus alpha or whatever variable that you wish. So if you look back at the root locuses, we can see that this could happen only in the case of positive locus, and it happens whenever the branches meet each other at the breakaway point. So at the breakaway point, we know the value for the poles. So here we have minus 0.5, and for this one we need to obtain the value of Kp. We need to see what would be the value of Kp in order to have such a behavior. So remember that the characteristics equation that we have is this expression 1 plus rho times n divided by d equal to 0, and for which we have two conditions. Condition on the amplitude, which says us amplitude of n over d is equal to amplitude of minus 1 over rho, and also we have the phase or the angle condition, which we don't consider right now. So according to this amplitude condition, we can obtain the value for rho, and then accordingly we can obtain the value for Kp. If we replace the n and d with the expressions that we have, we will have 1 divided by S2 plus 0.1s. And if we set S2 0.05 minus 0.05 and replace the values here, the value that we will get will be equal to 1 divided by 0.0025, and this should be equal to minus 1 over rho. However, we know that the value of rho in this case should be positive, because it happens only in the case of PL. So from there we can say that from here we can say that rho is equal to 0.0025. And since our Kp is equal to 200 times rho, from here we can say that Kp is equal to 0.05. So if we have Kp equal to this value, we will have both poles of the system located at the same place, which gives us the critically damped behavior for the system. What's the next question? Here we need to find the steady state error E infinity to the input of ramp, phi ramp t, for the same closed loop system. So for the same closed loop system means that Kp will be equal to this value that we have obtained, and then we need to determine the steady state value for R. Okay, so we can say that now the Ls that we have can be expressed in this format. Yeah? It is rho times 1 divided by S times S plus 0.1. And since the value of rho is equal to what we have obtained here, we can just replace it over there. Sorry. Okay. So we will have for Ls, we will have 0.0025 divided by S times S plus 0.1. And we want to calculate the steady state error for the input of RT equal to 5 ramp t, or equal to 5 t ut. If you want to calculate the steady state error of the system for the input type of ramp, since our system in this case is of type 1, because we have one pole at the origin, we can say that E infinity in this case for r equal to ramp will be equal to 1 over kv, in which kv is equal to limit of s times ls when s goes towards 0. We can calculate the value of kv. So kv is equal to limit of s times 0.0025 divided by s multiplied by s plus 0.1, and from here kv will be obtained as this will cancel out, s going to 0, we will have kv equal to 0.025. And from here we can say that E infinity is equal to 1 over kv, which is 1 over this value that we have obtained, we have calculated, and accordingly the steady state error E infinity will be obtained as 40. However, keep in mind that this steady state error is obtained when R or input is TUT. It is the unit ramp. However, in this case we have 5 ramp T. So think about it and try to figure out what will be the steady state error in this case. Okay? And the last question for this example is that find the range of values of Kp in R such that the closed loop system is bistable. So we want to analyze the stability of the system. Again, we can write the characteristics equation, which is 1 plus rho times 1 divided by s multiplied by s plus 0.1 equal to 0. And then if I rewrite it, we will have s2 plus 0.1 s plus rho equal to 0. Then we can just construct the Rouse table for this equation, s2, s1, s0. Here we will have 1, rho, 0.1, and rho. And if you want to have biboy stability for the system, we need to have all the elements in the first column of Rouse table be positive. Yeah? So from here we can say that we need to have rho bigger than 0 in order to have biboy stability. And if you refer to the root locus that we have for our system that we have obtained, as you can see here, we see that in the case of positive locus, as soon as rho or Kp is bigger than 0, our system is biboy stable because all the poles, both of the poles of the closed loop system are located on the left hand side of the imaginary axis. But in the case of negative locus, whenever rho becomes negative, our system will be unstable. So this is consistent with what we obtained according to the calculation. So this is the end of the example. However, please draw the root locus for this system using MATLAB. Compare your results with the results that we have here and then send me a copy of your results. Alright, that's all.